Great, thank you. I'm Alan Lavoie. I'll be presenting history-dependent domain adaptation, and this is joint work with co-authors from Google Pittsburgh, Matt Odie, Nathan Ratliff, and Dee Scully, who's here today. So the main idea of this paper is that standard methods in machine learning are often too myopic for the domains they're applied to. So typically we're focused on minimizing errors now and in the future, but many times machine learning is applied to systems which have an expectation of consistency over time. So I'll start by giving an example, and then I'll formalize the problem just a little bit. We'll go over some of our proposed solutions, and then we have some experimental results. So you can think of a system where we're employing a classifier that gets retrained periodically over time. And between each retraining, we get a mix of old and new examples. You can think of these as slightly perturbed examples, or maybe we just want to test to see if our classifier has learned something new. But the key is that we have a small additional cost for making the same errors we've already made, but a much larger cost for making new errors. And one intuition for this is that humans are manually correcting errors through some process. So if we think of two of these systems, one which has a classifier which makes consistent errors, that is, the errors between retrainings are the same, more or less. And we think of another system which uses a classifier which every time we retrain makes a distinct set of errors. There's going to be a big difference in the amount of human effort to maintain this system. So if we think of this blue rectangle as our feature space, and these pink circles are errors made by classifiers on previous retrainings, and the red circles are errors made in the current classifier. If we have a system with a classifier that makes distinct errors, over time we're going to make errors on many more data points. So this is going to represent a huge human cost for maintaining this classifier. And if it's bad enough, we might as well just not be doing classification. Whereas if we have consistent errors in the classifier, we're going to make many fewer incremental errors. And over time, we're going to get a much smaller space of misclassified examples, corresponding to a much lower human cost. So in general, we have a loss function which depends on our previous classifications. And specifically, we looked at the case where there's a low cost to repeating errors. But the key is that we have incomplete feedback, and that human corrections take time. So even if we do get corrections for points, which is definitely not certain, it's going to be delayed quite a bit, and we may need to retrain several times before we have any feedback. So the question we wanted to ask is, can we learn while minimizing new errors, even if we don't know what the old errors are? So our first method is quite simple. It's a good baseline. We just took a linear combination of previous hypotheses. And exponentially weighted averaging is almost trivial to implement. And we were using linear models, so averaging weights is equivalent to averaging classifications. And this gives us a simple baseline. It's also a fairly intuitive method in that we can think of classifications as a random variable, and by taking a linear combination, we're reducing the variance. So that's going to decrease the chance that we're going to change our classification. We also tried several kinds of warm starts. So the idea is that we have some hypothesis, and we want to make some updates to it, but we don't want to update it too much. So we can use fewer optimization steps, or we can use smaller step sizes. And more generally, we can use any online learning algorithm with the caveat that we don't want to update too much. In general, online learning would say, we have a function and we want to fit it as well as we can given this new data. Whereas here we're saying, we want to fit the function a little bit better, but we also want to stay consistent. So effectively, we're using a different loss function. We're training with standard loss function, and our actual loss function reweights the errors that we make. We also tried a weight nearness constraint. So here we're doing a full optimization, but with a hard constraint. So we can start out with a prior hypothesis, WT. We train a small update with length, say at most delta, and then we can add that to a previous hypothesis and get this constrained update. Finally, we tried adding several regularization terms to the optimization. So we have two different things we tried. One was a squared error, which says the predictions of the current model should be as close as possible to the predictions of the previous model. We also have a hinge term, which says the predictions of the current model should have the same sign as the predictions of the previous model with a maximum margin. And this is actually equivalent to virtual examples in the training set. So instead of using the true classification of the point in the training set, we would add points with the classification given by the previous model. And these are going to be weighted in the sense that if we have some coefficient of the regularization term, then that's also the weight we would want to use on the virtual examples.
The variable is WT plus 1. What's the thing that you change, WT plus 1? That's the thing that you want to learn?
So you can think of WT plus 1 as retrained from scratch. And then, so we have a whole list of weights that we've retrained from scratch. And we just want to make sure that we're close to the previous weight vector.
And HT of X is a sine of WT of X?
Oh, that's the, so we can think of hypotheses or weights. So the previous hypothesis would be including averaging. So we're not just using the previous weight vector, we're using it with averaging. Or not averaging, sorry, I'm in the wrong domain. But yeah, it's just the classification of the previous hypothesis. And that's actually classification, not inner product. As far as evaluation goes, we actually have two things we're looking to optimize. First is we want a discriminative model, and this is sort of instantaneous performance. So you can think of, in comparison to a baseline, we want to make sure that when we're constraining the model updates, that we're not constraining them to the point that we're inhibiting learning. So we want to do well in comparison to an unconstrained model in terms of discriminative ability. But at the same time, we care about the consistency of the system. So we measured this with cumulative unique false positives. And it is false positives and not just cumulative error. He has a great analogy to trying to drill oil wells. So if you're predicting which places are good to drill, and you have a false positive, this could be a huge cost if you actually drill down and test for oil. But once you've already drilled, there's no extra cost to having a classifier which tells you should drill here again. Because you're probably not going to go back to the same place and drill another well. False negatives also have some cost, but there's not the same permanent cost to correcting them. So this is why we used cumulative false positive. Well, the actual reason we used it is because at Google on this data set we determined that the cost was higher, but that's a good analogy. And this is sort of a measure of overall performance of the system. And the exact definition is if we look at the sets of false positives made by the each of our hypotheses, this is just the union of those false positives. And in either case, we're allowing hypotheses to be trained on all of our previous data, but we're only going to test them on our new data. in that so AUC would be calculated just on the most recent set of data that was seen, and we're only going to update cumulative mean false positives for that newest data. As far as our actual data goes, we used a Google data set, which is adversarial advertisements. And this is a sparse and a very high-dimensional data set, which is one reason we use linear models here. We also, unfortunately, that data set's not public, so we also use a malicious URL identification data set. This is put together by Justin Ma. And this is qualitatively similar, but it's a public data set. As far as the actual results, so each of these plots, the x-axis is the number of times we've retrained, and the y-axis is the performance of the models relative to a control. So the thick black line is our control, and this is percent difference, so that's at 0. On the left, we have the cumulative mean false positives, which is a measure of the system performance as a whole, and this is our instantaneous discriminative ability. So you can see that weight-based methods did quite well. We get about a 40% reduction in cumulative mean false positives on this data set. And we actually increased AUC slightly, but in general, we're just hoping not to change it too much. So that was a little bit surprising. What was also surprising is that our regularization terms did not work out. They didn't work at all on this data set. And one hypothesis we have is that it's not difficult to come up with a hypothesis that is close to a previous hypothesis on the training data, while still giving wildly different results on test data. So one way to fix this would be to actually use unlabeled data to get a better estimate of the regularization term and actually avoid overfitting it. So that's filed under future work. As for malicious URL classification, we see very similar results. So the weight-based methods did quite well. The regularization terms actually worked out a little bit. And here we are decreasing AUC, which is slightly comforting, but we're not doing it to any extent that's non-trivial. So this is actually a 50% reduction in the cumulative unique false positive rate. So you can think of the cost of maintaining this system in terms of human time required, we've about cut it in half without seriously changing AUC. So that's a really interesting result. And just to summarize, we presented the problem of history-dependent domain adaptation, where our loss depends on our previous classifications, and this has many real-world applications. We've evaluated several solutions, and we got up to a 50% reduction in cumulative unique false positives while maintaining a very high AUC. But there's lots still to do. So there's obviously very little theory in this talk. Why do certain methods outperform others? And can we do better? I don't know of any theory that says there's an absolute trade-off. And indeed, for a lot of these methods, we found that there wasn't an absolute trade-off between instantaneous performance and overall system performance. So that would definitely be an interesting area of study. And also, where can we make use of unlabeled data? So I gave one example of our regularization terms. We think there may be a couple other places we can use unlabeled data. So that's it. Thank you.